This sphere doesn't exist, which feels a little bit like a weird statement because clearly it's right there. Clearly we can see it. It's even shaded, there's some light hitting it. But what I mean when I say this sphere doesn't exist is that this is just a 2D quad rendered by Bevy. It is effectively 4 vertices constructing a plane. So what we've effectively done here is we have a camera in the Bevy world that is a 2D camera that's looking at a flat quad. And on that flat quad, we've applied a shader that draws pixels onto the shader, or onto the quad rather, to make it look like there's a sphere there, based on some fake sphere that we've defined in our code. I probably put this in the title, but this is a sphere constructed by signed distance functions. Now, this isn't going to be a super thorough intro to SDFs, as they're called, but suffice it to say that this sphere is defined by its center point and its radius. So you can think of this sphere as kind of the 0 point being the surface, whereas points inside of the sphere will be negative and points outside of the sphere will be positive. And the value of those points will tell you how far you actually are from the surface of the sphere. So obviously that can be a little bit much to visualize in your head. So let's get into the code. There isn't too much Rust code here. So to start out with, we do have a custom material. That material is called the SDF material, which is a material 2D that we've used the material 2D plugin to kind of install into our Bevy app. That material 2D for SDF material uses a single shader for the vertex and the fragment shader. So both of those functions are defined in that one WGSL file. And critically, we have to specialize here because we want access to the UV coordinate. The UV coordinates being for our quad, since it's a 2D shape. If we imagine this VS Code window as being the quad, because, it's also a rectangle, in the top left, we would have 0, 0. In the bottom, we would have 0, 1. And then the top right, we would have 1, 0. So like the UVs cover the entire surface that we're trying to look at using a range that is a float 32 from 0 to 1. So 0, 0 top left, 1, 1 bottom right, something like that. Not all systems use the same coordinate system, we'll call it, or the same direction for one of the components. For example, up and down might be negative. In another system, down might be positive. Regardless, for us, in our fragment shader especially, but I've enabled it for both of them, we need to push the vertex UV's shader def into this fragment shader, which will give us the UV coordinates inside of our shader for this quad. And we'll see why that's important later. Back in main.rs, in our Bevy app, we've of course set up the ability to watch for changes in the shader because hot reloading is fun and who wants to restart their app all the time? We've got the default materials, the SDF material, and then a setup function. The setup function spawns in a material mesh 2D bundle that is a single quad. That quad is scaled up to 512, and we apply our SDF material. In this case, it accepts a color, which I am not currently applying because I have more work to do on this example actually. And then we have a camera 2D bundle. So we've got a camera looking at a flat quad that has a shader applied to it. And that's what I mean when I say that this is like a sphere that doesn't exist. We are only looking at a flat plane or a flat quad or whatever you want to, however you want to model that in your head. There is no actual geometry there. So at the top of the file, I've got some constants. We'll go over what those are a little bit later when they're relevant. I've imported a couple of the functions and bindings from Bevy that are super useful. And I've set up our custom material with the color. I could probably call this SDF material. So I'm just going to change that now to SDF material. That is in group 1 binding 0. And that's it. The vertex input and output and the vertex shader itself, the function, actually doesn't change anything from the default. So it's what you would get otherwise. And then we have a number of utility functions here. I am going to skip those and talk about the fragment shader first to use that as a jump off point to talk about what these utility functions do. So in our fragment shader, remember, for every fragment, or you can mentally model that as for every pixel on the screen, even though it might technically not be a pixel, it might be a group of pixels or a half a pixel or something like that. For every pixel on the screen, we are going to arbitrarily set the position of what we'll call the eye. So in this example, we aren't even using the camera position that we've set up. The camera position in Bevy, we don't care about. All we're doing there is looking at a flat 2D quad. And inside of our shader, we're constructing a fake camera or a fake position for our fake camera. So we place that at some fake coordinate like 002, and then we tell it to look at 000. So in world space, in like the normal 3D coordinates that you're used to talking about, we have a fake camera at 002 that is looking at 000. We can then construct a transformation matrix so that any vector that we have in world space, we can convert into this view space or this eye space. This is super important because the way that we are going to be working with rays and the way that we're going to figure out what pixel needs what color is we're going to send out a ray from the camera towards every pixel using the UV coordinates. And to do that, we want to be sending everything in the right direction at the right angles, etc. So this builds us a matrix by which we can multiply things, or specifically multiply vectors, so that they transform from something like world space into this new camera direction. So the code that I've used here partially came from ShaderToy, which is why the UV coordinates here need adjusting. I'm not sure what the conventions are in other systems, but the conventions on ShaderToy seem to be that the UV coordinates have 00 in the middle, while our UV coordinates in Bevy have 00 in the top left. So if we take the UV coordinates from 0 to 1, we multiply them by 2, so 0 will stay at 0, 1 will go to 2, and then we subtract 1, we get UV coordinates from -1 to 1. So that means that -1 will now be in the top left, and 1 will be in the bottom right. Again, due to the ordering of some of the math and some of the helper functions, we also need to flip the y-axis to get this to look correct. And this is just a translation because I took some of this code from ShaderToy, because I took it from a system with different assumptions. We have to sort of bring it into the Bevy world because Bevy does coordinates a certain way. After that, we can calculate a ray that comes out of the camera or out of the eye. We do that by taking the matrix transformation that we previously constructed and multiplying the UV coordinate alongside the number, in this case 2, and then normalizing it. So just gives us a direction for a ray coming out of the camera, hitting a pixel and continuing. I feel like in this moment, it might be useful for us to explore what it looks like for this number to change. So if we, for example, use a smaller z value here, the sphere will get smaller because we're changing the direction that the rays are being cast in. So while we are thinking of this as our fake camera hitting a pixel coordinate and continuing, we can actually adjust, because everything is faked by us, where those rays are going. So you can see if we bring this up to 4, the sphere will actually fill the screen, and 3 makes it a little smaller, and 2 sort of gives us a full view of the sphere. This is actually where our camera is, so that makes sense. Based on the direction that this ray is going, we need to check whether the ray actually hits the sphere or not. So we take the position of the camera, or the eye in this case, and we take the direction of the ray that's shooting out through some given pixel on the screen. So if it was shooting out way over here at 00, it would clearly miss, but that's what we're checking here to see if it's going to hit. But for us, remember, we've recentered 00 on the middle of the screen. So in this case, 00 hits right in the middle of this sphere and obviously hits the sphere. So that makes -1, -1 up here, the new miss. We take this ray hit info, which is a little awkward. The ray hit info returns 2 values, the second of which is actually an ID if it hits something, which we'll talk about in a little bit. So we use this ray hit info, which will give us sort of the closest object to our ray position and whether it hit something or not. We pass in that info again, we pass in the position of the camera, and we pass in the ray direction that we calculated from the camera. And that gives us back a color, which we render onto the screen. So all in all, what this is doing is sending basically rays or vectors out of the camera in a specific direction. And if those rays hit the sphere, then we pick a color for that pixel based on whatever we want to, really. So let's back up a little bit. We've got an SDF sphere here, but the first thing we actually do is call this calculate transformation matrix to make our sphere a little smaller so we can see the code. So if we go to calculate transformation matrix, we open the code here. The really, really interesting part here is that we construct this matrix by taking the origin of the ray, so the position of the camera, the position we're looking at, and in this case, the role of the camera, which we're kind of going to ignore a little bit. I do feel that it's really interesting to note, however, that the code for constructing this transformation matrix is the exact same code, or extremely similar in any case. All of the core pieces that matter are the same. It's the same as the transform lookat function in Bevy. So this function called lookat does the translation minus the target, the cross with the forward vector, and a normalization, a cross with the right vector, and then constructs a 3x3 matrix from right, up, and forward vectors. And if we look at the code here, we're doing kind of reversed here. We're doing target position minus ray origin, which is just kind of a conventions thing, right? Then we cross that with, in this case, the roll, but it's effectively the same thing. The Bevy code just doesn't handle this roll like this. And then we cross right and forward again, and we end up constructing a 3x3 matrix with the three vectors that we care about. So we've got right, up, and forward. And this gives us a matrix with values from 0 to 1 that we can use to take one vector from world space and map that vector into eye space or view space. Now, if you've worked with Bevy quite a bit, you might notice that there are actually types for view space. If we go to the Bevy repo and we go into the Bevy PBR crate inside of the source render directory inside of mesh view types, you can see that there's a struct here called view that gets bound for us if we import these files. That gives us a view projection for our camera and a view in the inverse view and a projection in an inverse projection and the world position of our camera and basically everything we should need to do this calculation anyway. But remember that we aren't currently using the camera from Bevy in world space. So that's why we're still calculating this inside of the WGSL file for our fake camera position. I do intend, because you can see that I'm already starting to experiment with it, I do intend to use the camera position in Bevy land and map that position and the projection into this WGSL code, but I haven't quite figured that out yet. So it doesn't exist yet. So after we calculate this matrix, the next function that we hit is the check ray hit, ironically, which takes the position of the camera or the position of the eye and takes the normalized direction of the ray. So the ray as a directional piece, not the ray as a vector that goes to a specific place in the world or something like that. This is just for kind of mentally, this is equivalent of mapping the angle of something. So the ray goes out in a direction, and this normalized version of the vector will tell us what angle that goes out in. So check ray hit is a lot. Basically, what this function is doing is looping using one of our constants, because the functionality for ray marching is done by taking the ray direction and then increasing the ray a little bit and checking to see if it hit anything, and then sending the ray a little further and checking to see if it hit anything, and sending the ray a little further and checking to see if it hit anything, over and over and over until we tell it that it took too many steps. And that's really the only way that a ray knows to stop. So this defines how many steps our ray can take, which we've defined up here. In this case, it's 100 rays, which is 100 rays per pixel on the screen. So you can see where this would get computationally expensive, we'll say. So with that knowledge, this code is fairly understandable, is the way that I'll phrase it. It's a couple of if statements. It's this one loop. And now that you understand what this is actually doing, is it's taking a step and taking a step and taking a step until it's told to stop or it hits something. I think the only thing that we would need to understand is the return value. So as we'll see in a second, every SDF object, in this case we only have a sphere, every SDF object in our scene has an ID. So that's what the second value is here, is an ID. If it never hits anything, that ID is set to -1. If it does hit something, we just have set these to positive integer values. And then we also keep track of the final distance traveled by the ray, so we know how far something is by the time it's hit. So we get that vec2 back as ray hit info. So it's the distance to the object and the ID of the object. And then we need to calculate a color. Before we calculate a color though, I do want to go back into the ray hit because there is one more important function to know of, and it's SDF world. SDF world will tell you basically how close you are to an object in the scene. So if we look at SDF world here, it's pretty simple because we only have one object. We have the SDF sphere construction and we pass in the ray position. So in our case, this is the ray position of the ray as it's moving through the world. And if we look at the SDF sphere, this is literally the math for how to draw a sphere inside of 3D space somewhere as a signed distance field. So we've got some position. In this case, it's 0, 0, negative 0.4, which is where our sphere is. We've got some radius, which in this case is 0.9. And the core of this is we take the length of some vector and we subtract the radius from it. So what this is doing is it's taking some position in space as the center point of the sphere. And when we subtract the radius from it, because we're using the ray position in this calculation, subtracting the radius from it will tell us how far we are from that sphere. But the length calculation only gives us the distance to the center point of the sphere. And when we subtract the radius, we move out to the surface of the sphere. And what this does is it gives us positive values for the distance outside of the sphere surface and negative values inside of the sphere. So we can actually tell how far we are from the surface of the sphere from the inside or the outside. And then we give it an arbitrary ID of 1. I do want to mention that, make this a little bigger, I do want to mention that there is well-defined formulas for quite a few SDF objects. So once we've written all this ray tracing code, we don't actually have to care a lot about what kind of objects we place in our scene. So for example, here's an SDF sphere, which takes some point and some radius and does exactly the same code that we just had, except this is done in isolation rather than against a position in space where we might be. So that's the length of the position minus the radius. And here's an example for a box. You can do round boxes. You can do framed boxes, toruses, capped toruses. Of course, these just keep going and going and going. There's like a ton of formulas for SDF objects that have been calculated already by other people, especially this one page that we're on right now is an Ego's page. So let's scroll all the way up so that you can see this is an Ego. And they also have YouTube videos on the construction of some of these. And even further on this page, they go into alterations and combinations and extrusions and all sorts of interesting SDF combinations. For example, here's an SDF of a sphere with a rounded box where you can take the sphere out of the box or take the box sort of out of the sphere but remove the outside pieces, computing the intersection, as it were. And all of this is fairly reasonable math. So for example, the intersection of two SDFs is just the max function on the two SDFs, which is really interesting. So I'll link this page in the description because it's really interesting and they do a lot of very cool work with SDFs. And of course, there are primitives on, say, Shader Toy, both from Inigo and from other people, as well as more interesting SDF shapes that I encourage you to go look at. In many cases, these will really tax your GPU, is what I'll say. So if you scale this up to 4K, it will run at like a couple frames per second. It won't be running at 60 frames per second. So that's our sphere and that's our SDF world, so to speak. So at this point, we've calculated a ray out of the camera. It's shot off into space. It either hit the sphere or it didn't, and we now know that. And then we need to calculate the color. Of course, the vec2 that we calculated for whether the ray hit the sphere or not is an XY vec2. So the Y value gives us the ID of the thing that we hit. In this case, the Y value for 1 is the sphere. The Y value for 0 or less is nothing. So if it didn't hit anything, then we get a vec3 of zeros, which is black. Otherwise, if it did hit something, we calculate where it hit that thing by taking the position of the camera, adding the distance of the ray to it, times the ray direction. So this will give us the scaled ray plus the position of the camera, which gives us the position of the hit. We use this extra function called getNormal of surface to get the normal, and then we pass that information into color sphere. GetNormal is a fairly straightforward function, especially due to SDFs being like they are. Basically, in this situation, because we are working with SDF geometry, we can do something that is basically a very small change in the positive and negative directions for all XYZ coordinates. And then we just normalize those and we pass it back. And that turns out to actually be the normal of the surface that we hit. So mentally modeling this, you can imagine that doing a larger change maybe on the x-axis versus the y-axis will give you a different amount of change in each direction. So if we are on the surface of something, right? If we're on the surface of the sphere and the x-axis points directly into the center of the sphere, then the change will be more drastic than if we're going in the y or the z directions, which will go along the surface of the sphere or the tangent of the surface of the sphere. And that because we are working with SDFs and because these changes are being calculated based on the distance to the SDF surface using this SDF world function, we just get the normals. I'm not going to say for free because we have to calculate it, but we just get the normals for what feels like something that shouldn't do it for us, in my opinion anyway. So we have the position that we hit the sphere on, and we have the normal of the surface. So we have the direction straight out from the surface of the sphere where we hit it. That gives us the color sphere function. In the color sphere function, we fake some light. We do a lot of faking in this code. So we pick a position for the sun, which is 143. We pick a color for the sphere, which is 100. The direction of the light then is from the sun to the position of the hit. So we normalize that to get the vector direction from the sun to that position. Using a dot product, we can tell for that vector, that direction, how similar the light direction is to the normal of the surface. And that is what a dot product is. It's how similar are these two vectors. So if it goes negative, we zero it out, because if you think about directionality, if one is in the same direction as the vector exactly, then you can flip that vector 180 degrees and imagine that that's -1 for the amount of similarity that you have. So it's either exactly similar, or if it was perpendicular, it would be 0 similar, or if it was exactly in the opposite direction, it would be -1 similar. So we take how similar these two vectors are, and we multiply it by the sphere color. And then just because we can, we modify the color a little, just to make it a little nicer, so we don't get pure black, if that makes sense. So we just add in some random color here, basically, by adding two vectors together. And that's how we determine the color. We do it by the positive component of the similarity of the vectors. And of course, I just realized why the other GPU examples for the SDF examples were running so slow. It's because I never got rid of my SDF example, and my GPU was already occupied. It turns out if you run two GPU heavy processes at the same time, they compete for GPU resources. Who would have thought? In any case, you can see how if the light is above here, somewhere to the top right, the color changes as the angle of the normal points in a different direction. And that's it. That's an SDF sphere in Bevy. I'm hoping to take this and do a little bit more with it. I have a ray marching example to render volumetric materials that I would love to finish. This is actually a step on my way to doing that, because I realized that in that other example, in the volumetric materials one, I actually have the Bevy camera, which I'm trying to work with, and a 3D bounding box that I'm trying to work with. And I'm trying to use those numbers. So I need to get this to use the Bevy camera positioning first, and then I can move on to that. So I'm going to do more work here. We'll talk about SDFs again. I find them really interesting. I think that the things you can do with them is super awesome. And a lot of the really interesting or really awesome shader toy shaders use SDFs. So we'll do that more. I hope you enjoyed a peek into SDF spheres and ray marching. This code will be up on GitHub. If you have questions, you can leave it on the video, on the GitHub. Both work. I will probably respond slower if you put an issue on the GitHub repo, but you can totally do that as well. And eventually I might get to it. But I will see you in the next video.